As future engineers, we have been tasked with finding a solution to challenges faced in engineering in order to better society and improve our way of life. Out of the grand challenges presented by the National Academy of Engineers, we have chosen to take on restoring and improving urban infrastructure. As many of us know, Texas's East Coast was hit by a major catastrophe that impacted everyone one way or another. Tropical Storm Harvey struck the coast of Texas on August 17th and is the second costliest natural disaster worldwide. Perhaps the most devastating aspect of Harvey was the flooding it brought upon to the Houston metropolitan area. The amount of rain that fell upon the city of Houston was too much for our stormwater infrastructure. As a result, the Army Corps of Engineers began controlled releases to alleviate the amount of water in the Addicks and Barker reservoirs to prevent the water from breaching over the sides and damaging additional neighborhoods. However, it was too late. The releases flooded homes surrounding Buffalo Bayou, and the Addicks Reservoir still reached capacity and started to spill out. In order to prevent such catastrophe from occurring again, my colleagues and I have created a program that gathers Houston's rain data and the Addicks Reservoir data in order to present the user with plots that show a relationship between the two. Seeing this relationship can give the user an idea how the amount of rain affects the water level in order to predict the amount of rain needed to reach a critical level. Having knowledge of this helps engineers predict when a controlled release will be necessary before it becomes too late, like during Tropical Storm Harvey. In order to accomplish this, we first gathered an extensive amount of data that spanned over a couple years to get more accurate plots. Secondly, we had to format the data we gathered in order to be analyzed correctly by the code. We did that by first converting the dates of the Addicks Reservoir water level to numbers using loops and conditionals. Then it creates a matrix of the converted dates with the corresponding water level in 15-minute intervals. Finally, it creates a new matrix with the maximum reservoir level as the water level for that date. After the reservoir level dates are formatted, the code moves on to format the precipitation data dates in a similar manner as before. Third, all of the data is synchronized into one matrix to make data manipulation easier. Fourth, a built-in function is used to sort the rows from greatest precipitation to the least, which also sorts the dates as well. Based on the amount of precipitation data, it is ranked accordingly and only counts the days with rainfall. For our dataset, number 1 are the days with the maximum amount of rainfall, which happens to be when Houston was struck by Harvey, and number 120 are the days with the minimum amount of rainfall. The plot shows the cumulative amount of rain and how the reservoir level is affected based on the current water level of the reservoir. We also include how close the water level was to breaching the sidewalls and how long it would take the reservoir to drain back to normal. Now I'm going to run the code. The code initially takes a while to run due to the amount of data we have provided. Once the code is finished running, it prints out a formatted output statement that tells the user how much usable rain events are in the data. To clarify once again, we use days that actually had precipitation. The code continues to tell the user that the rain events have been organized in descending order and instructs the user to input a number between 1 and 120 in our case. Inputting 1 gives data plots during Harvey, since that is the most amount of rain Houston has ever experienced. As you can see, as the amount of rain increases, the reservoir level increases exponentially. That line in the fourth plot is the maximum height the reservoir can safely handle before going over the sidewalls. During Harvey, the water did breach over the sides on August 29th. Additionally, if we choose to select a new rain event and insert 120, we can see a drastic difference. With the minimum amount of precipitation, the reservoir level stays practically level. The lines are plotted on the same graph for comparison reasons. The program also lets the user know how close the water level was to breaching the sidewalls and how long it would take for the reservoir to go back to normal levels. Our program is limited to past rain data to show the correlation between rainfall and the reservoir levels, so it can't be used to predict future reservoir releases or reservoir levels. However, if the weather forecast calls for a certain amount of rain, then the engineers at the reservoir will know how the reservoir level will behave and can plan accordingly. Our program can help prevent the reservoir from reaching its brink again by taking data from the past and learning from our mistakes by letting engineers know in time how much rain the reservoir can handle before a controlled release is necessary.